Matrix. Welcome to your physical sciences show on a Tuesday. I was telling Tracy I haven't been here in so long on a Tuesday, but if you've forgotten who I am, I'm Looney, and that is Tracy.
Well, they've seen me. Maybe not last week, but, you know, they've seen me. They know who I am.
How are you?
Good news.
I'm good.
Yeah, she was calling me short, which is quite funny because she's smaller than I am.
The kettle. Calling.
It's okay, I'll get over it.
It's fine. It's fine.
Yes,
What are we doing for the Matrix
Okay,
today?
guys, what we're going to do today is we're going to do acids and bases, okay? Now, this first part really is going to feel a little bit like, well, we're rehashing some stuff you maybe did in grade 9, some stuff you probably did in grade 10. You didn't see any of this last year in grade 11, so just stick with me, okay? Today's a lot of theory. Next week, we're going to hit the calculations. So this week, we're just keeping with theory, basic stuff, and then next week, hitting the calculations. Make sure you can use your calculator.
All right.
Yeah.
I'm sure they can. Mindset is,
I hope
please,
so.
don't you come here without knowing how to use your calculator. What is that? Anyway, guys, I'm calling Tracy Shorty because she stands on a platform, but you guys can't see it. But I also once had to sit on my chair, which was on a platform. So don't worry, Tracy. We are in this together.
Alright, I got it.
How to get a hold of us, guys. Facebook.com is our Facebook page /LearnExtra. And then our Twitter handle is @LearnExtra. And then now talking about calculators. If you want to win yourself this awesome Cassie calculator, all you need to do is complete the test yourself section from our notes, the link for the actual entry form, and where you fill in all your answers and all your details is on our Facebook page as well, guys. So you just click on that. For grade 12s, you have your entry form, and you stand a chance to win this awesome calculator from Casio. And remember, entries do close on Friday at 12 in the afternoon, so you have all the time in the world to enter. So please, guys, just, thanks.
It's great. And do the test yourself on this section, guys.
Yes.
We chose questions that hopefully bring a lot of the theory together. So make sure you do it because it's actually quite important.
Yes.
Okay. So can I get going?
Yes.
Okay,
Periodic
good.
table.
It's all my show now. Okay. Ooh.
That's what I was saying. It was
Wow,
like
look at
periodic
that.
table.
Okay. So that's what the board thinks of all of this. So we're going to start with acids and bases. Anyway, moving on. Guys, what we're going to do today is we're going to define different definitions of acids and bases. And there's a couple, and we'll talk about them. We're going to look at the properties of acids and bases, and not just the normal ones like like an acid is sour and a base is soapy, but some of the other chemical properties that are very important. And we're going to look at some of the reactions. And including in that, we're going to include some terminology. Sometimes in acids and bases, what makes it feel more difficult is we've got lots of funny new terms here, okay? Remember when you first started organic, so many of those terms felt a little weird, okay? Same thing, okay? So just stick with us. But before we do that, here's the challenge question for today, and it's a multiple choice question. But if you go and answer it on the Facebook page, which is what we'd like, I want to know your reason. Okay, so this one's got a bit of a twist in it, so I don't just want to know if it's A, B, C, D, or E. No, there's no E, but I want to know why. Okay, why maybe you didn't choose the others, etc. So, which of the following statements is always true about monoprotic acids? A, the amount of dissociation, let's say, of a weak acid and a strong acid is the same. B, a strong acid produces more H+ ions in water. C, the pH of a strong acid is always stronger than the pH of a weak acid. And D, 1 mole of a strong acid gives more H+ ions in water than 1 mole of a weak acid. Okay? So, there you have it. Okay? There you have it. Those are your things. So the question is, what is always true about monoprotic acids? Amount of dissociated weak and strong is the same. Strong acid produces more H+ ions. The pH of a strong acid is always stronger than the pH of a weak acid. And 1 mole of a strong acid gives more H+ ions in water than 1 mole of a weak acid. Okay? So you need to be thinking about that as we go through. So let's just get going. Now, the first thing we're going to look at is our basic properties of acids and bases. So starting with acids, okay. Now, the thing here, oh, look, pen has decided it doesn't like me. So, acids have the following properties, okay? They are sour, they taste acidic. Hopefully not too many of you done this, but what kids do is they like to eat things around them, and so some of you have possibly eaten ants, and ants are sour. When you're little, did you? No, never mind. It's not something I would do.
Okay.
Okay, and flying ants are a delicacy. I know in upper middle Africa somewhere they actually fry them. I had a friend who liked them. Anyway, she got very excited when flying ant season came about, but that's besides the point. Anyway, they conduct electricity in a solution because they create ions, okay? They can neutralize a base, okay? We're going to talk about neutralization and titrations very specifically next week. For now, it reacts with a base, and it produces a metal salt. Now remember, grade 12s, a salt is just a classification of a compound. Doesn't mean it's making table salt. That doesn't mean it's making sodium chloride. It simply means it's making a compound that is ionic, okay? Which means that salt is a metal plus a metal and a non-metal bonded together, okay? So be careful there. And water, and there's an increase in the concentration of the H plus ions. Those H plus ions we often are actually H3O plus ions, the hydronium ion, okay? Because when the acid ionizes, we get the H3O plus ion at the end, but that becomes difficult to say all the time, so we just keep it as H plus, but it's the same thing, okay? The H3O plus ions. Then, a base, in terms of its very basic properties, bases have a bitter taste, and this is another thing some of you would have done as children. It's one of those things. It's how we learn, it's how we explore, it's how we learn about the world around us. We try and eat soap. Did you ever do that, Looney?
Yes.
Yes, of course. Okay, and now it gets hard because now we have liquid soap, so we've got to be really careful.
I tried liquid soap and like soap.
Oh,
both.
wow.
Yeah,
That
I was one
explains
of
a lot.
those children.
Moving on. So, but it's got that horrible bitter, soapy. You can taste. It's horrible. All bases would taste like that if you could taste them. Remember, you don't taste things in the lab. They feel soapy, like soap. Okay. Even things like your really, really strong bases like sodium hydroxide (NaOH) feel soapy to touch. Okay. They have that slippery, slimy feel. They also conduct electricity in solution because they create ions when they dissociate. They neutralize an acid, so it's the opposite to an acid, okay? Creates a metal salt, same metal salt as we had before. It's an ionic substance, non-metal and metal bonded together in water. Alkalis, now here's a new term here, guys. A base generally is a solid, okay? Though, yeah, generally is a solid. If the base or a basic substance can dissolve in water, it is an alkaline, okay? It turns, we use the term alkali, okay? It's just a fancy term to say it's a base dissolved in water. Alkalis increase the concentration, now watch here, of the OH minus ions. H plus for acids, OH minus for bases, okay? And it is the OH minus ions concentration, or, and sometimes this is the way to look at it, it decreases the H plus ion concentration. Same thing, okay? So, that brings us to our definitions, and we have two. Grade 12s, you must know both, okay? And I am going to pronounce the first one and his name wrong. I'm sorry. It's just one of those things. There's lots of words I don't like to say in science, and this is one of them. One of the first definitions of an acid and base was done by Arrhenius, okay? And what he said was, for an acid is a substance that releases H plus ions in an aqueous solution. So, for example, when I have HCl, which now dissolves in water, okay, so we react it with water, what happens is we end up, we get the Cl minus ions, but we also end up with H3O plus, which we just write as H plus most of the time, okay? So every single acid has hydrogen in it. It has to have hydrogen in it, okay? Otherwise it can't be an acid. So this definition for an acid is great because it fits for every single acid. There is no exception to this. Then we come to his definition of a base. And he said a base is a substance that releases OH minus ions in a solution. that's okay when you are looking at sodium hydroxide. Okay, it's got OH in it. Okay, and when we say it dissolves, it ends up Na plus and OH minus. But what happens when you have something like sodium oxide? Sodium oxide is a base. Okay, it's an alkaline, it dissolves in water, reacts with an acid, neutralizes it. Okay, but when it does that, it doesn't actually create OH minus ions. So there's a problem with this definition in that it doesn't encompass enough of the bases. Okay, it's very specific to bases with OHs in them. And this is where the error came in. And this often happens in scientific processes. People give definitions, they have models, and then they do more investigation. Someone else comes along and goes, oh, hang on, wait, but it doesn't include this, or this needs to change. So what happens is now we have to have a definition that takes everything we know and makes it broader. Okay, so we can encompass everything. So that brought us to Brønsted-Lowry. Okay, guys, please, that O is written with an O and a little line through it because it's not English, and I can't remember which nationality they are. Okay, it's a combination of scientists who were given credit for this, and what they said is, and these are nice ones, these are the definitions, is they said an acid is a proton donor. By a proton, they mean an H plus ion. And now you say, oh, hang on, wait, Tracy, H plus ion, how's that a proton? Remember, hydrogen only has one electron and one little proton, and during a chemical reaction, along the way, it loses its electron, okay? So it says, bye-bye electron, and that becomes what we call a naked proton, okay? I call, in my classroom, hydrogen is the flasher, okay? Because he's a naked proton. What can I say? It's very rude. But he's just, literally, the H plus ion is a proton. That's what it is, okay? So when I talk about a proton donor, I mean an H plus ion, okay? A base is a proton acceptor. Two halves of the same coin, basically. An acid gives its proton away, doesn't like to be on its own, so that proton gets taken by a base. You've done a little bit of redox in grade 11. Remember, redox reactions was the transfer of electrons. Okay, this is the transfer of protons. And because of that, we actually call this a protolytic reaction. Okay, proton. Okay, it's not an electrolytic reaction. We not have electrons. It's protolytic. So Brønsted-Lowry give us a much better definition of what an acid and a base is. Acid is a proton donor. Base is a proton acceptor. That's something you really must keep in the back of your mind when we get to the section on conjugate acids and bases, because you've got to look at your formulas and go, can I give away a hydrogen? Can I take a hydrogen? Okay, and how does it change? So what I think we're going to do is, that's a good place to have a quick break, I think, and then we're just going to do a little bit more theory before we hit some of the questions.
All right, okay. Mindsetters, let's take a very quick break and we'll see you straight after this. Welcome back, Mindsetters from...
Sorry.
I'm so sorry, guys. I can't...
My fault.
Tracy! Okay, anyway, guys, I'm sorry you didn't see that. Tracy dropped something and then she came running and James was like 3, 2, and she's still here and John was still there. It was just like a whole thing. But I hope you guys are still enjoying the show. Guys, if you remember, a few weeks ago we had Raven in studio with us. That very cool guy, very clever guy, scientist. He's like 25 years old. He's doing his master's. Yes, I remember. Master's in some awesome bio something. But guys, he's doing his presentation tonight actually. So I hope you guys will be on our Facebook page. I'll post all the details. He's part of the Fame Lab fam, and he's doing his presentation tonight. Remember, he told you that he entered a competition and then he got a chance to go overseas. So today he's doing his presentation, and we want to send him all our support and all our love. I'll send you all the details on our Facebook page about what you need to tweet. We need to send Raven all our love so that he knows South Africa is behind his back and we're supporting him, and that all the mindsetters love him, and that we want him to do the best that he can. I'll post all the details on the Facebook page, all the hashtags, everything you need to say, so that we can just, pump him up and psych him up for tonight. Raven, hope you remember him.
Well, I hope they do too. He was here 2 weeks ago in the studio with
Yes.
us. And Abram interviewed him.
Yes.
Just so you know, I just broke the pen
Yeah,
for
no,
the board.
it's
but
fine.
it's okay. I'm having one of those days. I also tripped over my own 2 feet in front of my grade 9s today, so it's all right. Anyway, we can get on with it. So, we're now going to look at the concept of conjugate acid-base pairs. Guys, they go together. Now, conjugate, don't get too caught up with these words, okay? But what this means is, during an acid-base reaction, an acid gives away its hydrogen, and then a base takes it, okay? So when we look at HCl, for example, it's not dissolving in water, okay? We're not worried too much about what's happening in the water, but it turns into H plus and Cl minus, okay? The HCl is an acid. You're happy with that, okay? H plus, don't stress too much about that, because H plus is still actually acidic in property, okay? But when I look at the Cl minus, this is what I said to you before the break. We've now got to consider, is it in a position to give away an hydrogen, or is it in a position to take a hydrogen? Cl minus does not have a hydrogen. It cannot give a hydrogen away, which means it cannot act like an acid. That means the Cl minus has become a base. And HCl and that Cl minus are what we call a conjugate acid-base pair, because we have the acid, which has become what we call a conjugate base. Okay, it's its pair. Which then means, okay, when a base accepts a proton, so OH minus, that's my base, okay, accepts this proton during the reaction, H plus, we form water. Water is most definitely in a position to give away a hydrogen because it's got H2O. Okay, water is also a special kind of compound. We'll get that in a second. So OH minus is the base, and H2O becomes its conjugate acid. Okay, so an acid turns into a base, and a base turns into an acid. They become the opposite of what they were originally. But how do we show this? Okay, so here we've got one that's a little more complicated, which I really hope you can see. It didn't come out that great. We have HNO3 and ammonia, nitric acid ammonia, both of which you should know are an acid and a base. Okay, now what happens is that ammonia gives, ooh, look at that, it's just going to be, ooh, didn't want that either. Oh, it's going to get fun from here on out. Okay, guys, if I'm not here next week, we know why. All right, because I broke the equipment. So, the nitric acid gives its hydrogen away, okay, gives it to the ammonia. Because that HNO3 has now lost its hydrogen, it becomes NO3 minus. The ammonia has taken the hydrogen and become NH4 plus. Remember, that's a dative covalent bond. You did that last year. In terms of pairing, the HNO3 is my original acid. The NH3 is my original base. Your products are your conjugates. Okay? So products become your conjugates. So your acid turns into a conjugate base, and your base turns into a conjugate acid. Okay? Because they go together. NO3 minus has no hydrogens to give away, but it definitely can take a hydrogen to become nitric acid again. Ammonium ion NH4 plus will not take any more hydrogen. There's absolutely no space, but it can absolutely give that hydrogen away. Okay? That brings us to amphilites. Amphilites are pretty much compounds with a little bit of an identity crisis, okay? So an amphiolite, here's the definition, is a substance that either acts as an acid or a base, depending on the other substance it's reacting with, okay? Water is the best amphiolite we know, because when we look at water, okay, water, when it acts as an acid, is reacting with ammonia. Ammonia is a base. It can never act as an acid. Acts as which means the water has to be an acid. When water reacts with HCl, hydrochloric acid, it acts as a base. Okay? So this little water is very confused. It doesn't know what it wants to be. Here, it's giving a hydrogen away, and here, it's taking a hydrogen. So it has the ability to do both. And how it acts all depends on what it's reacting with. Okay, so that gets us to the concept of the strength of acids and bases. Definition. A strong acid is an acid that ionizes almost completely in water. So we get a very high percentage of ionization. We have lots and lots and lots and lots and lots of ions. Okay? And in particular, the ions that we're looking for are the H3O plus ions, okay? That's a high concentration of the H3O plus ions, okay? Or H plus ions. A weak acid ionizes only slightly, and we have a low concentration of H3O plus, okay? It doesn't dissolve very well, basically. For a base, generally, we say that bases dissociate. Bases generally are ionic substances like NaOH, KOH, all of those. Sometimes, though, they have to ionize because they're a covalent substance like ammonia. Okay? And a strong base ionizes almost completely in water. And when we talk about a high percentage of dissociation, that actually means it gets lots of ions. Now, here it's a little more difficult to go concentration of OH minus ions because they don't have to necessarily create the OH minus. So be careful there, okay? A weak base dissociates or ionizes only a little bit. It's as simple as that. Okay, it doesn't like to dissolve in water. Then, reactions. Guys, you must know these. This is also where being able to write formulae, recognize trends, these general ones are so, so important because when it comes to the calculation part of this section, if you can't write the balanced equation, you can't do the calculations. And they are going to want you to write balanced chemical equations. Okay, so you must learn these general ones, okay? An acid plus a metal gives us a salt plus hydrogen. The hydrogen comes from the acid. Whatever the non-metal that was bonded to the acid now bonds to the metal. Acid plus metal oxide. Oh, wait, look here. Salt plus water. Acid plus metal hydroxide. Salt plus water. Do you see a trend? We always make a salt. The difference is what comes with the salt. Okay. Number 4 is the nice one. It's actually probably one of the easiest ones to balance. Is an acid plus a metal carbonate. Remember, metal carbonate means it's got CO3. Hydroxide means it's got OH. Gives me a salt, water, and carbon dioxide. We've got a third one. Okay, gives off gas, gives off carbon dioxide. And then the neutralization reaction, which is a titration. We're going to discuss those next week in a lot more detail, okay? Acid plus base gives me a salt plus water. Metal oxides, metal hydroxides are acid plus base reactions, okay? Though metal oxides and metal hydroxides are basic. When they dissolve, they're also called alkalis. And then we get indicators. I didn't want to put it all in here, but guys, indicators are quite important, and you really should know, hopefully by now, things like litmus will turn red if it's blue litmus in the presence of an acid, and it goes blue in the presence of a base if it starts off as red litmus, okay? Then there's a whole bunch of others. There are hundreds of different indicators. Indicators are basically a weak acid, this is the definition, in equilibrium with its conjugate base. When we mess with that equilibrium by adding acid or base to it, that equilibrium shift causes an acid change. Okay, and there's lots of natural indicators, by the way. Black tea is a natural indicator. Red cabbage juice is a natural indicator. Lots of them, but they change color. They change color, though, at specific pHs. So it's not just a case of, well, if it's under 7, it'll be this. If it's over 7, it'll be that. Some of them only change color when it's under 3 and above 3. Some change it under 11 and above 11. So it all depends, and we'll talk about those in more detail next week, because you've got to be able to choose correct indicators for reactions. Okay, so let's jump into a question. Okay, so what we have here is, let's look at the first one. And if you look at the notes, they're actually from papers from long time ago, because this section was always examined, and then they changed it a bit, and now it's back. And I go, yay. Okay, so adapted from the Transvaal paper. Okay, so this was before we had all our 9 provinces. Don't get too stressed about that. Nitrogen dioxide, okay, and sulfur dioxide can be prepared according to the following equations, respectively. So here's the first one, copper plus, please remember that those two together give me HNO3, okay, HNO3, don't worry about the balancing. That gives me copper, essentially gives me copper nitrate, NO2 and water. Then we have here, this is sodium sulfate, Na plus, okay, it should be Na2SO3, sulfite, sorry, and hydrochloric acid, and that gives me hydrogen sulfite and sodium chloride, or salt, okay, and water. Now they ask you, what is an acid-base reaction? Definition, straight definition. An acid-base reaction is a reaction in which there's a transfer of H plus ions, or it's a reaction in which there's a transfer of protons from the acid to the base. That's what an acid-base reaction is, okay? Transfer of protons, okay? Now, I chose this very specifically because I needed you to see some things, okay? In terms of what's happening with a whole bunch of stuff. Now, they ask you, which of these two reactions is an acid-base reaction? And now some of you are going, okay, Tracy, we don't even know where to start. So let's take some of my scribbling out and let me help you. Okay, let's consider equation 1. Okay, now equation 1, I have a metal and an acid, okay, and I said to you that the general reaction with the metal and acid is that we should get a salt and we should get hydrogen gas. Okay, so now we look at this and we go, well, Cu2 plus and 2NO3 minus together give me copper nitrate. That's a salt, but what's the problem? I've got NO2 and H2O. So I'm really starting to think, not so much. Another thing we need to look at, okay, the copper over here, this little bit of remembering stuff from grade 11, has no charge. The copper over here is now 2 plus. The copper lost 2 electrons, okay? The copper loses 2 electrons. And the copper, the hydrogen over here, the H plus, doesn't actually do anything. So first of all, I've got a loss of electrons here. There's a change in oxidation number. That immediately tells me it can't be acid and base. Okay? So it can't be number 1. Let's check for number 2. Sodium sulfite, that's the salt, okay? And hydrochloric acid, we don't know the general one for this, but let's see what happens. Okay? Now, watch what you see here. This is H plus, okay, and Cl minus. Watch what happens. The Na plus stays Na plus. That's not a problem. The sulfite actually takes this hydrogen from the chlorine in order to create the hydrogen sulfurous acid. Transfer of protons, transfer of H plus. The chlorine loses its poor little electron, becomes Cl minus. Poor little chlorine, okay? So, answer to the question, number 2. Okay, now, they say to you, write down the acid-base conjugate pairs. Obviously, you need to have identified the correct equation, okay? Now, when they ask you this, and I so didn't leave myself enough space, so I'm going to do it over here. Please be careful how you write this. You want to make it very, very clear as to which is which. So rewrite the equation, and I've just got it here again so that I get it right. So we've got 2Na plus, okay, I'm not going to worry about the phases for now, SO3 2 minus, plus 2HCl, and then we've got H2 SO3, 2Na plus, and we have the 2Cl minus. Now, first and foremost, did anything happen with the sodium? No, sodium plus. She's just there. Okay. So, we realized that the hydrogen was given its, the hydrochloric acid was given its hydrogen to the SO3 2 minus. Okay, which means the HCl is an acid. Okay, that's my acid. And the SO4 3 minus is my base. The NH plus, the Na plus is a spectator. It's there because I needed something to keep the SO3 2 minus company, but it's not actually changing. The HCl gives its hydrogen to the SO3 2 minus, sorry. That makes this here become an acid. So this is a conjugate acid, okay? I'm not quite finished yet. And the Cl minus, which I've squeezed right in at the end, has become, I'm just going to put Cb conjugate base. I'm still not done because they wanted us to identify the pairs. The HCl goes with the Cl minus, and this is my conjugate acid base. Ooh, just pretend that's a T. Oh, wow. Should not have broken the pen. Okay, conjugate. But I write faster. Acid, base, pair. Okay. And then your other one is the SO3 and the H2SO3, and that's also a conjugate acid base pair. Guys, you want to make sure that your examiner knows exactly what goes with what. Write it out. Okay? They just said identify the pairs. That's what we've done. Okay? Here, the better you do, the more accurate you are with identifying this, the better it'll be. Okay? So be careful when you work through this. Now, along the way, we've actually answered the last question, because the last question said to us, identify a spectator ion in this reaction. It's the Na plus. Okay? Just like in redox reactions, which you've done a little bit about, we can have spectator ions. Proteolytic reactions can have spectator ions. Okay, ones that are there, but they don't actually take part, so they don't change anything. They don't gain or lose hydrogens. Nothing happens to them. They're the same on both sides. Okay, now I think it's time for another break.
All right. Guys, before we take a break, I'd just like to read this from Mary Ortiz. I think that is her name. She says, please, Looney, do me a favor. I'm Mary Ortiz and I'm new to Mindset. I want to send a shout out to Latifa Mahasa. She made me like this page. So I want to show her that I'm watching all the time. So thank you so much. And shout out to your friend. And thank you, friend, for inviting her to our page, because we're trying to get to 80 likes. And thank you for watching and keeping your promise. We support mindsetters like you, and we hope you're enjoying our shows. So with that said, guys, let's take a very quick break, and we'll see you straight after this. Hadi. Welcome back.
Okay, and I worry about me sometimes. I don't think I need to. I'm quite normal. I've decided after that. Just putting it out there.
No, it's just, yeah.
Okay, should I teach, Looney?
Yeah.
All right, let's go back to the teaching song, because I don't know what she's doing. She's having her own little moments, and we'll come back to it just now. Anyway, so now I have another question, and this was from the House of Delicates, which no longer exists, by the way. and it's a paper too, and I'm going to
Don't fall now.
I'm
Hey.
going to fall off my platform. Let's not go there. When HCl is bubbled through distilled water, it ionizes. Oh, look, that's the eraser. It ionizes as a result of proton transfer. Okay. The equation for this ionization process is given, and this is actually a really important equation. You're going to see it lights. So what happens here is the HCl comes along and it actually gives its hydrogen to the water. Now we say this is ionization because HCl hydrochloric acid is a covalently bonded compound, which means as a covalently bonded compound, it isn't made up of ions. So when I force it to become ions when I dissolve it, it's ionization, okay? We're not dissociating ions from each other, we're ionizing it, we're forcing it to become ions. And what happens is we get H3O plus and Cl minus. Now, first thing they say to you is provide a suitable name for the H3O plus ion. Okay, that doesn't mean John or Mary or Sue or whatever. Okay, that's not what they're asking for. They're asking for its scientific name, and hopefully you guys know this. It's hydronium. Okay, H3O plus is known as the hydronium ion. Okay, it's a hydronium ion. Now they say to you, what causes the solution to have acidic properties? So when we look at this, we go, okay, what is it about this part of the product side of my solution that says, why does it behave like an acid? What is it that makes it acidic? It's this. It's the presence of the H3O plus ions. Okay, those H3O plus ions, that's what it's that ion that makes acids corrosive, that makes it so dangerous, okay? And the more of those there are, the more dangerous it becomes, okay? So it's an acidic property because it has the H3O plus ion, and we've had hydrochloric acid, HCl, okay, well, it's hydrogen chloride, it's in gas form, donate its hydrogen to the water, okay? Then, would the resulting solution be strongly acidic or weakly acidic? Now, it's not the wording's a bit unusual, but what they're asking you is what we get a strong acid or a weak acid? Now here, this is where it's actually really important for you to, and I'm pretty sure your textbooks have lists of the most common strong and weak acids and bases. Please, you must know them. Hydrochloric acid, HCl, is one of our strongest acids that we use, okay, besides phosphoric, okay, and sulfuric. So it's a strong, phosphoric's not, anyway, moving on. It's a strong acid. The point here is because it's a strong acid, when the HCl ionizes in water, it produces a lot of H3O plus ions, okay? This is strongly acidic. There is a very high concentration of H3O plus ions in the solution because the HCl ionizes almost completely, okay? So what we'd want in there is, first of all, your answer is that it's strongly acidic. Why? Because there's a high concentration of your H3O plus ions, okay? Because HCl ionizes almost completely. Sure, my handwriting just gets better and better. Almost completely. See, I can't spell too. Good. Okay, now, what do we call a reaction in which proton transfer occurs? Well, I said to you earlier, this is a protolytic reaction. Okay, it's a protolytic reaction. And I know Looney is busy refreshing all the pages because I know there's millions of questions. Am I correct? Yeah, there's lots of questions. But before we do that, let's go to the challenge question, okay? Looney, did we have some attempts at answering it?
I can check quickly.
She's going to check
Because now I'm
for us.
on your questions. You see, now you're asking me to do some
She
other-
can't do two things
Oh,
at
yes,
once.
we've got like 22 attempts.
Okay, anyway,
What's the answer? Oh, you haven't even... Okay.
I haven't given the
I was going to give you some of the answers that we have on the page.
Yeah, let's hear what they said.
A, it
Okay.
is because a monoprotic acid only donates one proton and hydrogen.
Yes.
And hydrogen atom, and it is related to the number of dissociation each molecule has. Then Nelly goes D, and then
Yes.
Shaylan says C, and then Mlungisi says D, Senzo says C, Cebise says A, Vincent says C, Jessica A, Mashabo A, Zenzele A, Nomonde B. It only donates 1 hydrogen plus per molecule in an aqueous solution. Abel says B. Porzo says B. Strong acids ionizes almost completely. Should I carry on?
No, it's good.
Okay.
It's okay. So the point here is we have a wide range.
Yes.
Okay. And this is why I gave this as the challenge question. There's only a couple who actually got it right.
All right.
Okay. And this is how we're going to go through this. Okay. So I'll give you the answer as we go along. Number 1. So which of the following statements about monoprotic acids is, now here's the key word, always true? Okay. First of all, the amount of dissociation of a weak acid and a strong acid is the same. That is never true. Okay? Because what that statement is saying is whether it's a weak acid or a strong acid, it's going to dissociate the same, it's going to ionize the same, we get the same amount of particles at the end. Not a chance. So A is never true. We leave it out. Then they say a strong acid produces more H plus ions in water. Yes, but we've left out one very important concept here, and that's concentration. Okay? So this is sometimes true if I'm comparing it to a weak acid, but it depends on concentration. So if I have a very concentrated weak acid with a very dilute strong acid, I can possibly have the same number of H plus ions in the water. Okay? Depends on concentration. So B isn't always true. C, they say the pH of a strong acid is always stronger than that of a weak acid. No. Once again, it depends on concentration. They can be very similar, okay, but it depends on concentration because your pH is determined by the amount of H plus ions we've got, which you're going to see next week, okay? So far we haven't done so well, have we? But then we get to D. 1 mole of a strong acid gives more H plus ions in water than 1 mole of the weak acid. Absolutely. Okay? 1 mole, these are monoprotic acids, which means they only have one H plus to give away every time. But your strong acid ionizes almost completely. So when you compare 1 mole to 1 mole, it's a you're keeping lots of stuff about the acid and base the same. So that the strong and the weak acid the same, which is 1 mole of each of them. You get more H plus ions from the strong acid. So the answer is D. That was mean of me, okay? But I did it deliberately, and that's what you should be thinking about when you do multiple choice, grade 12s. Because multiple choice can get tricky like this. Because sometimes there's a little bit of truth in what they're saying. So be careful, please, okay? All right, so Looney, let's deal with some questions.
All right. Olebogang Serebe is asking you to repeat question 2.2.
2.2. Okay, let's go find it. So 2.2 was what causes the solution to have the acidic properties? The H3O plus ions. It's the presence of the H3O plus ions. Okay, that is what gives us the acidic properties, what causes it to be corrosive and all the rest of it. Okay.
Okay, this is not a clear question, but
okay, we'll see what we can do.
Tonic Mogohlwane is asking you to help her, balance equations.
Okay, sweetie, we can't do that today. All right, what I'm going to suggest to you is maybe go onto the website, go to the grade 10 stuff, and look for the videos and the notes on balancing equations. Because that's really grade 10 stuff, and I could spend the next hour. That is a skill, so you need to practice it. Go, and if necessary, maybe even ask your science teacher to give you some notes, maybe doing it in the grade 9s, give you the notes she gives to them to help you with that. Okay, sweetie?
All right. Our website is learn.mindset.co.za. tonic, then you can just go there, check out the stuff. And then Tabiseng is asking you, is it possible to get a conjugated base and a base as an acid-base pair on the previous question on H2SO3 and SO3?
No. They're called conjugate acid-base pairs because you must have an acid with a base. Okay? Because remember, and we'll just go to a blank page. So, for example, if I have H2SO4, okay, and I'm not writing all the equations out in full, but when it gives away its hydrogens, okay, it turns into, and let's say it's given away both, SO4 2 minus. This is a pair, they go together, okay? This is your acid, this is your conjugated base. Okay, you cannot have a conjugate acid-base pair that's not an acid and a base. Okay, they have to go together. If you look at ammonia, okay, and I'm doing all sorts of things. Ammonia, when it gains a hydrogen during a reaction, becomes NH4+. Okay, that's the pair that goes together. Ammonia is a base, its conjugate acid is the NH4+, because now it's in a position to give a hydrogen away. So they have to go in acid-base pairs. Okay?
Okay. And then this is from Vincent. When defining acid-base reaction, if I say it's a neutralization reaction, would I be wrong?
It's not enough, because a neutralization reaction is a special acid-base reaction. So if you tell me an acid-base reaction is a neutralization reaction, you're sort of saying the same thing twice, because a neutralization reaction is an acid-base reaction. An acid-base reaction is defined by the fact that there's proton transfer. Okay, so it's that H plus ion that's been moved. Just like when we did redox in grade 11, it's defined by the fact that there's electron transfer. So when they ask you to define the type of reaction, they want the mechanism. What's happening microscopically, okay? And neutralization is just a special acid-base reaction.
All right.
Okay.
Oleboheng Seribe again. Can you please explain what is meant by a spectator ion?
Okay. A spectator ion like the one we did in question 1, okay, which was, is that question 1? There we go. Okay. Our spectator ion here is the Na+, okay? Now, what it's done is the SO3 2 minus. In reality, I can't just have SO3 2 minus hanging around as a charge. Charged compounds don't exist, okay? That SO3 2 minus must be bonded to something to make it stable, which in this case is the Na+. When the reaction takes place, the NH+ is there, but it ends up as NH+. So it started as NH+, and it ended as NH+. So it's there to help the reaction happen, but it doesn't take part per se, it doesn't change. It's like a spectator in a soccer match, okay? With the new World Cup coming up, we all know spectators are important to the match, okay? Because they add atmosphere, it makes it all that much more fun. But if I walk into a soccer match as a spectator, I walk out like I am at the end. I don't change into a soccer player, which would be scary. But I don't change. Okay, so I'm there because it helps the situation, but I don't take part. Okay.
All right.
Yeah.
I'm not sure if this is also what you're going to answer to this person because of that other question.
Okay, we'll see what we can do. Yes.
This is from Kellet. So how do we balance an equation when it has 2 minus? What do we consider to balance such an equation?
Okay.
Same thing.
Yeah, I know, that's also the same thing. Sweetie, with the 2 minus, you don't ever, this is the quick one with balancing, you don't ever look at the top numbers when you balance it. It's the ones at the bottom. Okay, you guys need to go get some new notes. That's very, balancing equations, so important.
Oh,
so important.
And then James Baloy is asking, does HCl aqueous conduct electricity easier than H2CO3 aqueous?
Better than carbonic? Yes, because, okay, that's actually a really nice question. Okay, so the question is, does HCl conduct better than H2CO3, carbonic acid? The answer there is yes. Okay, and I'm pretty sure he didn't want just yes as the answer. Why? HCl is a stronger acid. So when it ionizes, okay, so basically when we draw the ionization, we draw it like this, Okay, we do the equilibrium a little bit different because we get a lot of H plus ions and we get a lot of Cl minus. When carbonate, jeez, my handwriting just gets worse. When carbonates ionize, it's the other way around. Okay, carbonic acid doesn't ionize very well. So we end up with H plus ions, and we might have 2 of them, but that doesn't matter. Okay, here it is about the strength of the acid. So the stronger the acid, the better a conductor it is, because there are more ions present. In order to conduct electricity, I need ions present. It's actually a way to test the strength of an acid per se. It's not great, but it's one way that you can do it. Okay.
Gochi Kwame is asking, is there a difference between acid-base reaction and proteolytic? Yeah.
Same thing.
If there is a difference, which one is the correct term for a reaction involving transfer of protons?
Both. It doesn't matter. If they ask you to identify the type of reaction and you say acid-base reaction, that's fine. Okay? You saw in question 2 that right at the end I asked you, what is this type of acid-base reaction? It's proteolytic. So if you tell me it's a proteolytic reaction, that's fine. It's the same thing. Okay. Basically. It's just acid-base is the normal English word.
Okay. Just going through the questions. Aldra Jingisane, thank you so much. Happy birthday to you. Happy birthday, happy birthday. And then another question, Siabulela. Can a polyprotic substance serve as an amphilite?
Absolutely. Good question. Some of you are doing acids and bases at school already. I can tell that. If my grade 12s are watching, they're going, don't have a clue. Okay, so polyprotic acids or something like H2SO4 has more than one hydrogen in it. Now, what happens when H2SO4 dissociates, okay, or is forced into ions? It actually does it one at a time. So we end up with HSO4 minus and H plus. Okay. Now this little H4 over here, HSO4, I don't know why I'm saying that, is now very confused because this now can act as an amphilite depending on what happens from here on, because it has a hydrogen that it can give away, but it is in a position to take this hydrogen back and become, so it's in a position to take the hydrogen back, therefore act as a base, or if I react it with something else, it can give its hydrogen away and act as an acid. Okay, so it's not quite sure where it wants to go. This is an amphilite. Okay.
Okay, no, it's fine now.
Are we done now?
Yeah.
Leonie's like, oh, I don't understand. Anyway, okay, because it's actually great timing. Guys, this is about learning the terminology. Great questions today. I'm glad. And I can see that you're learning, which is very, very important. Now, make sure next week you tune in because we're going to do the calculations. They're really not as difficult as they look. And if you're not doing core maths, but you are doing maths literacy, I will show you how to use your calculator because that's the important thing. Okay, so you don't have to get worried about the terminology. But it's very, very important for next week.
All right. Thank you so much, Tracy. Mindsetters, thank you so much for tuning in. Congratulations to Mama Tubandivo. You have won yourself this awesome Casio calculator. Use it wisely. Have fun with it. It's such an awesome thing to have. And remember, Mindsetters, if you're asking how to get past papers on our website, all you need to go is to go to learn.mindset.co.za and you'll find everything there. It's quite simple to use, man. But until next time from us, we love you.